In a previous video, I showed the mechanical advantage that you can get from different pulley arrangements. And this video is going to be similar. It's just that I'm going to be showing the mechanical advantage that you can get from a hydraulic lift. And most of us are familiar with hydraulic lifts because we see them in mechanic shops and they're used to raise vehicles. If you go online and look for videos about hydraulic lifts, a lot of times you'll see these models that people have developed. And these models will be used for lifting up toy cars. A lot of times they're used in science projects. And the one thing that I've noticed about this is that they're not really showing any kind of mechanical advantage. What they're really showing is fluid transfer. So basically transferring fluid from one spot to another and using that to lift the vehicle. And the reason I say that is a lot of times you'll see that they use syringes, but the syringes are of the same size. And you'll see as we go through this video that the syringes are going to have to be of different sizes in order to get a mechanical advantage. So this is a fluid mechanics problem, and what we're trying to solve for in this is what force P applied on the small plunger A is necessary to hold this system in equilibrium. In other words, how do we hold B, the larger plunger, steady? So if we remember that force is equal to pressure times area, then we're more than halfway to understanding why it is that we get mechanical advantage in this type of system. We can see that B is much larger, so we would expect for there to be a much larger force at B because it has a greater area. We'd also expect that if we push down with enough force on plunger A that we can get B to move upward. So here's a few parameters of this problem. First, plunger B weighs 9,000 pounds and the area that's in contact with the fluid is 600 inches squared. The fluid has specific gravity of 0.75, and that just means that it's 75% of the unit weight of water. Plunger A has an area of 6 inches squared that's in contact with the fluid surface. And again, we're trying to solve for that force P. So we know that in a static confined fluid, which is what we have here, the pressure is equal at all points at the same elevation. So you can see we've marked XL and also marked XR, and those two are at the same elevation. So we know the pressure in this system, it's static, meaning it's not moving, it's confined. So we know the pressure at those 2 points is going to be the same. We also know that XR is right at that interface of the plunger B and the fluid surface. So let's start by solving for that pressure at XR. So if we remember before, we said force is equal to pressure times area. If we rearrange those terms, then we know we can get pressure is equal to force divided by area. In this case, the force is going to be the weight of P, which is 9,000 pounds. And that's going to be divided by the area that's in contact with the fluid surface, which is 600 inches squared. If we solve for that, we get a pressure at XR of 15 psi. So we've solved one side of the equation. Now we need to go to the other side and figure out what the pressure at XL is. So we're going to start with the pressure under A, and that's going to be the force, right? In this case, we're neglecting the weight of A, but we're going to, for the force, we're going to use the force that's being pushed down on A. So that's P, right? We don't know that. That's what we're trying to solve for. And we divide it by the area, which is 6 inches squared. But we also need to deal with the pressure that's due to 16 feet of fluid from the bottom of plunger A down to XL. Okay, so we know pressure at XL is equal to pressure at XR. We know that the pressure at XL is equal to the pressure under A plus the pressure due to 16 feet of fluid, and that's equal to 15 pounds per square inch, which we had solved for earlier. We know that the pressure under A was the force P divided by 6 inches squared. Now the pressure due to the 16 feet of fluid it's going to be 16 feet times the specific gravity times the unit weight of water. Now, if we were to solve the numerator in that part of the equation, we're going to wind up with pounds per feet squared, but we're working in pounds per square inch. So that's why we divide by 144. So that way all of our units are uniform in pounds per square inch. I don't go through all the mathematics of solving this, but if you do, it's P is going to be equal to 58.8 pounds, which means that if you push down with 58.8 pounds of force on plunger A, you can hold this system in equilibrium. So that means that the force applied, that 58.8 pounds, it holds plunger B steady, which plunger B is actually 153 times the force that you're applying. And obviously, if you put more than 58.8 pounds of force on plunger A, you're going to be able to then lift plunger B. So hopefully you found this helpful. If you did, I'd appreciate it if you like it. That can get it out to even more people who may find this to be useful. And thanks for watching this video.